Hello, and thank you for joining me to be predicting power transformer health conditions. This is a regression problem, and we're going to focus on ensemble methods, but we're also going to look at a different way, a slightly different way to look at our correlation analysis, and then really focus on the error analysis. How do we improve our model after we've done our grid searches, we've done the best that we can? What else can we do aside from grid searches to improve our model? Okay. So we're going to get started on our regression machine learning problem. Okay, so getting started with just importing the standard data science libraries here, standard Sklearn PCA for pre-processing, train test split, our three ensemble methods, bagging, random forest, and gradient. And with the bagging, you can put in other models. So here we're going to use the ARD regressor and the K neighbors regressor with the bagging regressor. Okay. If you don't do that, it's basically just the same as the random forest. Okay. Slightly different, but basically very, very similar to the random forest. Okay. So importing the data from my GitHub reservoir here today. Okay. So run and then import the data from my GitHub reservoir. You should go download it if you want to, but you can just again import it directly from my library. And so actually just noticing here, just mention this. So we're installing scikit optimize, and we're going to do a Bayes search. So we're not just doing a standard grid search. We're going to do the Bayes search cross-flow validation. So you have to import this from scikit optimizer, SK optimizer, to get this one specifically. If you're using Colab, this does not come in the default library, so you just have to install it every time. That's what was going on there. So we're going to go into our data set. So I get bored of the standard colors. So I'm going to set palette right here. Set a palette to this color palette that I have up the top. I'm going to set style to this palette right here. So set style right here. So we have our X ticks. So set that to true. We're going to make grid. We're going to have grid color be kind of gray, I guess you would say. And then we're going to do two dots. It's going to be a dotted line. You can see it looks a little bit nice. This is maybe not the best one to show, but right here you can see nice dotted line. So it's a lot better than just the default. It's really nice to mix stuff a little bit. Just have, very simple to make your plot look different than the default. Especially with C1. C1 is really cool that you can just set this in advance and then change your style for the rest of your plots. And so what we're going to do here, very basic. We won't do any of this part. We're just going to do very basic kind of building a figure, his plot, title, and then shows. So this is just a distribution plot of all of our variables right here. So one of the things that you'll notice as you look through this, you'll see a lot of exponential distributions. So it's kind of, if you've been following my project for a while, you know I do not like exponential distributions. They're just kind of a little bit harder to deal with than most. So one of the things is when we deal, one of the common ways, one of the easier ways, depending, can be the easier way to do or to deal with exponential distributions is doing a log transformation. So in this next loop where we have doing the same thing, this is just to inspect it. So we're not making any changes right here. We're going to do the same thing. We're going to look and we're going to plot the distributions, but we're going to plot the distribution EFPs. We're going to plot it with np dot log. Take the log of each variable. Everything else is the same. We're going to do a log plus speed. So it's the log space plus speed. Okay. And then run this one right here. You can see here, and if you see the CO2 and the CO and CO2, so much better. These distributions, both of these are changed from our really exponential distributions that we had up here somewhere. Not super extreme CO, but CO2 is quite an extreme exponential distribution. Okay? So there we go. Okay. Then what we're going to do is go into standard kind of correlation analysis right here. We're going to do SNS map and we'll do df.core to get our correlation matrix. No, not heat underscore map, just heat. Adding my underscores just for extra fun, I guess. So here we have our standard correlation there. So you see that methane is highly correlated with ethane, ethylene, and so not many super high correlations or super negative correlations, but a lot of moderate correlations. But one of the things is we really want to put this in context of our target. We're going to be trying to predict the column health index. So let's just understand really what the correlation is with our health. This is not the only thing that your model can use in predicting it, but it certainly does help. Having linear correlations are usually the easiest for your model to use. So it's a good starting point. What's going to obviously be the best thing in our model predictions? What will add a lot just very easily for predictions. So we're going to do, I'm sorry, I'm talking while I'm typing. So sort values here, and then we're going to plot. So core width, sort values, and then plot. Okay, so we're gonna just to get it in the order. Spell core width correctly. Stuff. And do we see our thing that we're looking for, health index that has a high correlation with itself? Not a surprise. But we can see DBS and interfacial V have the highest positive correlation, and water content has the highest highest negative correlation. We have some kind of pretty moderate correlations right in the middle as well that might not be valuable to use in our final model. And some things to play with. So really, this gives us a test. Maybe we can get rid of some of these lower correlated ones and just see. It's a very simple test, but it can help. It doesn't always. It's almost too simple a way for it to really work. So just notice what we're doing here. So we're going to understand the partial correlations. And so what this means is we're going to control for another variable and then look at the correlation with our target, right? So we're not just going to do it kind of blankly, like just looking at the correlation. We're going to factor in that there's more stuff going on. And well, there's a whole bunch more that we're able to do, but we're going to factor in, if we take into account this other variable, what is really the true correlation, if we're factoring in the covariance of this other feature. Okay. So what happens in here, so what we're going to do, I install Pingouin, I think I'm pronouncing it Pingouin, library for some interesting mathematical, usually for correlation. So we're going to go Pingouin, too hard to use this one, Pingouin. I guess it's French, I'm not really sure, I'm not really good at pronouncing that. And then what we're going to do, I'm bad at English or French or, we're going to import it as PG. And that's just the standard. Even the library that I would say is very common, but this is the standard default set values for this. So to look at this, we're going to do PG dot partial underscore core. We're going to do, taking from the Seaborn library data DF, we're going to go X equals DBS. We're going to go Y, our target, equals the health index, and covariate is the one we're going to control for. So we're controlling for the covariance of water content in this one right here. And so as we read this, we get the number of samples, we get our R squared. Again, while we're controlling for the other feature, we get our confidence intervals, and then our p-value. So this is kind of a handy thing just to understand the p-value. So as we control for the other features, if we get a really low p-value, that means the probability that this correlation is not significant is very, very possible, right? So if we have a very low correlation or a very low p-value, means the chances that it's not significant are very, very small. So if we get a low p-value, that means that this correlation really is valid as we control for the other feature. So a couple, but we could do this individually, but Pythonists. And so what we want to do is we're data scientists, so we can do this in a way. So what I'm going to do, I'm going to get really I use this just to have the column name and a couple of things, but I'm going to drop the health index because when we're doing this, we can't have health index also be the correlation that we're controlling for. So I needed to not have it in the index as we go through this, and I'm going to use df dot, just spoiler, dot columns right here. So I'm going to use the column names from this, and I'm going to use that a couple of times just to help us with this. So just a quick, easy way to get the column names truthfully. Okay, so what we're going to do is we're going to make two blank in our loop, kind of standard loop. We want to start with a blank list. We're going to start with blank data frame. P-values, data frame P-values, data frame R squareds, right? So we're going to get our R squareds and our P-values. Okay? You can do a complex interval as well. Okay. What we're going to do here is we're going to look at df.columns. And then df.columns. Okay. So what we're going to do is when we first do this, we're going to first create blank lists. We're then going to iterate through the second column, and we're going to append 0 if B1 is equal to B2. We're going to say they have the 0. This is the p-values. For the p-value and the r value, we're going to just put 0. We're just going to put a placeholder. We could put 1, I guess, for the r squared, but just putting in placeholders right there. So when it's the same, because you can't run this calculation, the partial when it's the same value in here, right? So what we're going to do is we're going to do in this one right here, we're going to go pg dot partial go up here, partial underscore correlation, or sorry, core, and then data equals df, x equals b1, so the feature that we're looping through, and then what we're going to do in the outside loop, we're doing b1 first and then b2 second. So we're going to go b1 once and then go everything in b1, do all of the comparisons and see how the health index really lines up. As we control the health index, as we control for the other features, really what are our squareds as we control, and what are our p-values and r squareds. Okay, it's a little bit of more of an intense correlation analysis, but it gives a very robust understanding. So here what we're going to do is we're going to do blocks. So we build our data frame, our result data frame. This thing is so they're not by block, just blocks. So we're going to select a Pearson, the one row that we have. But just so that we get to the one value right here, we're going to select out our p-value and our r squared. So we're just doing block right here, our location. And then what we're going to do is we're going to do p dot concat. P dot concat. So we're going to basically kind of like the append for doing a data frame in a loop, but that's what we're going to do. So we're going to run through this one time, and then after this loop is done, we're going to be outside of this. We're going to have this full built list right here of p values and r squareds. And what we're going to do then is append, and then we'll go to the second item in column number 2. We'll iterate through all of the columns in that data frame just for the second item, then all for the third, then all for the third. And we're testing all of these, controlling for the variance properties. Just going to set the column names, because just by default the column names will appear, and so we're going to set the column names equal to our df1, and so if we run this, make sure it all runs nicely, and columns, and I just am pretty bad at spellers and things. Columns, C-O-L-U-M, spelled right one time and not the next time. Okay, so that runs, it doesn't take too long to run that. What we're going to do, we're going to do bigger next. I'm going to set a heat map, no underscore this time. We're going to set a note equals true, format FMT, so we just get 2 decimal places right there. We're going to go CMAP equals to SNS, just to do something different than standard SNS dark palette. Don't usually do dark palette in this, but it makes sense in this one. Look, dark underscore palette, and we're going to give it the first color from our palette as is true. So gotta make sure I spell these things. So don't look like I know what I'm doing. As CMAP. So with CMAP, as CMAP equals true. If not, you would have kind of blocks for each color, and then kind of more jagged, just limits for each one. This has a nice smooth color tone all the way through. It's going to be a little bit more detail, I guess you would say, from this. Because the interesting one to note here is the power factor seems to have really high p-values. This is the p-value. So what this is saying is hydrogen and power factor. So when we control for hydrogen, the power factor doesn't seem to have a very valid relationship with our correlation. So this would be one of the features that we want to remove. I kind of talk about this as well. We probably want to try at least experiment, and I did experiment with and without this power factor. Okay. You can see here's some other ones. Another one right here, the nitrogen seems to have quite a few high p-values, 0.09. Not as extreme as the 0.08, but still above the 0.05 that we consider. Yeah, this is a little bit more than a random chance that it's pretty unlikely that, well, it's a little bit unlikely at least that they have a high correlation, that they have a high true correlation. Okay. And so here what we're doing is the DBS. DBS, you can see around 6. So if you look at it, gives us a better sense of really the correlation, but while we're controlling for them, while we're thinking about that, really it's not just happening between these two variables, there's more stuff going on. And we need to factor in all of the other things in our data set to really get a good sense of what the true correlation is, if there's anything, any bias added to that. Okay. We're going to do a heat map here. We're going to do light palette this time. Okay, we see that was true. We're going to do, I added one thing here, line width. And so this is going to just add a little bit of spacing between it. It did not look good for the one up above, but it looks good when it's a little bit lighter color. So I did it here. And then going to plt.title, set font size to 20 and font weight to 4. We're then going to do, and this would be the X label, or sorry, this is the Y label. Controlling for this, we're going to set font size 50 and font weight again. We're going to do X label. Set the font weight, font size to 50, and then the font weight to bold. So you get quite a few different examples right there. Okay, great job. Let's make sure this runs. Okay, and so I left from our great friend ChatGPT. I asked a little bit about really what should we be interpreting from the partial correlations, right? Because it's not, I mean, I was taught this in school, right? So it's one of those things that, well, I mean, in data science school, yes, but it's not something that you're taught in kind of if you're coming into this from outside of data science, just to give you a sense of what we're really trying to do with this, okay? And really, it's about determining what's important. And I would say at the end of the day, what it does is it gives you something to experiment with. It doesn't give you the answer. It gives you things to, I want to test if this works or does not. It's saying this one's not important. Let's actually take it out of the model then, or build our model, and see if that helps or hurts our final answer. Okay. So we're going to do some pre-processing. Okay. So now this is, so just to highlight here, you probably have done this before when you've taken the log variable. So you see we have lots of 0 values or very close to 0 values. We take our log and some really very, and there's some negative values. Well, below 0 or right at 0. Okay. So what we can do here is we can go transformation. So what we're going to do is we're going to take if you take the log of a negative or a log of a 0, it's going to create an infinity value, which is just not super helpful for what we're going to do, and we're not going to be able to run our model. So what we're going to do is we're going to take the min, we're going to say if it's greater than or equal to 0. So greater than or equal to 0. What we're going to do is, this is the complex part. So what we're going to do is we're going to shift, if it is at 0, we're going to just shift it a little bit before we take the log. So we're going to take log, so we're not changing our distribution, we're just moving it a little bit so it doesn't have that 0 value. It's going to be the same shape though. So what we're going to do is if it's less than 0, less than or equal to 0, the minimum value, what we're going to do is we're going to add 0.01 just to move it up a little bit. plus our min value, and we're going to times our min value by negative. Okay. So we're timesing our min value by -1, so negative 2 or something like that. It's now going to be +2 plus 0.1 to the distribution. So we're shifting it, and then just by a little bit more just to make sure. And we're going to take the log. And if it's not less than or equal to 0, we're just going to take the log. It's the kind of standard way. I got to run this list first. Okay. And so the list is from, you can see the notes that I identified above. These are the ones that I wanted to use that had exponential type distribution. So then after we do that, we also had some outlines that we had to do. So what we're going to do is we're going to take the log, not the log, the percentile, numpy.percentile of our feature, and we're going to get the 25th and the 75th percentile, or upper and lower two values. To get our interquartile range, we minus those two, and then what we're going to do is we're going to click lower is equal to lower times 1.5 minus 1.5 our IQR range. Upper is upper plus 1.5 times our IQR. So nothing really fancy. They're just basically not making any assumptions with our so now we can see our distributions. Got a little truncated going on, and it looks quite a bit better now. So you got distribution move it a lot in some places. You can see a little bit over here, but these distributions are all, they look much better for what's going to work on our distribution. Then we're going to choose. We also have a log ones a little bit further down. Our log ones, we did move a little bit, kind of truncating a little bit, but you'll see here much better distributions, much no exponential distributions. The average is going to really be representative of something in the middle of our distribution. It makes a log, which is usually going to be better for a machine. So let's go through all of these. So let's see if we have infinity values. And so we got out all of our infinity values in our data set. There's no infinities in our data. So it's really an important check, right? Because they're kind of, this is kind of the pain in the butt of doing the log transformation. If you have something at 0, it's going to do that. So what I found was for the final predictions, as you can see, I experimented with all of these, and you can play around with what works for you, right? So I found this works well. You can kind of say, maybe we'll use the log. The log works well for some of them, and I found that it didn't work well for all of them. But this is just my experimental process. Maybe you can find a better combination than what I have. Okay. And remember that we found power factor didn't look like it was suspicious, so that would be a good one if I wanted to try. That would be a good one to take out. I did find that it worked well. It did help a little bit, but it's something good for you to try. It might not always be the truth when we try with all of the other features, and that could have something to do with the control. Maybe we eliminate one of the ones that, when it was controlled, when it showed a high value, high p-value, we don't want to use that. Also, the tertiary correlation of the one that we're controlling for. This is do our train. So we make our features. We're going to pull those out from our data frames to make x and y our target, or features in our target. We're going to make x train, and I just do tr x underscore ts for test. I get very lazy. You always have to change tr and or train and test. This is something you can't get away from. And so it is just a lot. So it's just one letter you have to change. So train. I think it's very obvious what train and test, that tr and ts is kind of truthfully not super confusing when you do it like that. We're going to do train test split. And then what I'm going to do here for our error analysis, I'm going to need a copy of our x train so that I can add it to understand our analysis. And so I'm going to make a copy right here. I'm just going to save it for later, and you'll see how we use this later on. Then going to pull standard scalar, and we're going to fit that. So we're going to standardize our data. So we're going to make this and initialize the standard scalar object. We're going to fit it as we do that, and then we're going to transform our x train and then transform our x test. So we learn from the x test, and we didn't fit transform in this model so that we can transform the x, but then also transform the x test with the what's learned from the trained data set. Okay, to avoid data leakage. I just always spell everything incorrectly. Okay. There you go. Okay. So then I did as well do a PCA. It didn't, I find, help with this one. So I left it here though, because it sometimes does. It's one of those things that we don't know going in usually. I always experiment with PCA because it does often help, and so it's a good thing to include. I'm gonna experiment. So the workflow is set up so that we can experiment and just comment this out, and everything will work the same. Okay? So what we're gonna do here, we're predicting. We're gonna build a model evaluation function. We're gonna predict. We're gonna give it this model. We're gonna predict with the model that we give it. We're then going to go model dot. Sorry, not predict. This is fit. I'm gonna fit the model before we do anything else. Go model dot score for the train data, model dot score for the test data. Then we're going to predict on our X train. We're gonna plot that. So we're gonna make a resid plot. Resid plot. Okay. Resid plot right here. And then we're going to do a title, and then we're going to show. We're going to do that for train data. Then we're going to do a residual plot. So we're going to predict again, and we're going to do a residual plot on our test data. Resid plot. And then we're going to make sure that we return score train, comma, score S. I always take the vowels out of my variable, make them a lot shorter grade. I feel that they're still pretty easy. You might not if you're not used to it, but I will just remember it doesn't have the variables, right? And that's easy to remember. How did I spell this? Oh yeah, I spelled it without the variables. I kind of strictly, unless it's the first character that's a vowel, I will just not use vowels for the rest of it. It just makes it a little bit easier to follow and a little bit less running to do. So now that we made that function, let's initialize our random forest regressor. Get our model right as we do that, and let's give this to the model evaluate function. And you're gonna see we're getting a train and our residual plot. Okay. So then what we have here is that we have our gradients, and you can see it's making some pretty heavy errors right in this area right here. Do gradients, boosting regressor, fit this, give it to our model. This is the same thing. You can see it's kind of overfitting right here a little bit. It's having some issues in the same area right here. We're identifying some areas that potentially could be causing problems. So we're going to do our ARD or bagged ARD. So this is bagging regressor, and we're going to do our estimator. It's going to be ARD regression. And I don't usually play with any of the hyper features in ARD regressions. The default is usually the best. So we're going to fit this, and then we're going to go model. You can see here. Again, we're having some problems in this one little area right here. So getting it consistently. Keep that in mind when we're doing our error analysis. Simply target it around. That will make mistakes in. Okay, so we also have our bagging canon, and so we're going to do bagging again to estimator main for trouble spelling today. And we're going to give it our k neighbors. Okay, we're going to fit with that, and we're going to give this to the model. See, you make quite a few mistakes, right? So we're going through that. So then I'm just putting this all into a summary data frame right here, and we'll get into the. We can see our ARD just did not do very well this time. It looked a little bit better, I think, from before, but you can see here our I'm realizing that I don't think the test score was this bad the first time I did this. It really shouldn't be so highly negative. My guess is a little bit of overfitting now that we're experiencing. What I'm going to do is I'm going to try rerunning this now with now. I mean, one of the things that I saw that I was fitting this model twice. So fit here. I didn't realize I did this the first time I did the workflow. I didn't notice this. And I fit it again as I'm giving it to the model. So just to kind of leave the workflow, I'm just going to comment it out. And this is the great thing about reading a function. I'm going to comment out our model evaluates. Okay. So now that I got rid of that, we're not doing the overfit twice. This is the same score that I got the first time I run that. So we can see there is definitely some overwhelming fit. We do really well at our training scores and kind of like mediocre at our test scores. So let's see if we can do a grid search and improve our random forest and our gradient boosting are doing the best. So let's focus on those two and see if we can get those two up to much better. So we're gonna do our Bayesian search, Bayesian grid search, I guess you could call it. So we're gonna do initialize a random forest regressor, just a blank copy. We won't do all this, but we'll do n underscore estimators as one of the features that we're giving this, right? So we're going to iterate through all of these different ones. All right, 100 auto 2 2 2 100 auto 2 2 3 and try every single one of these. Well, it's going to be a little bit more targeted. It's going to go towards kind of what's working. So instead of just a grid, so that was the grid search, so we'll try every single one of these combinations. Bayesian is going to be a little bit more targeted and go kind of with what's working, right? So technically should be fast. I wouldn't say I notice a huge difference. I would say I do notice that's a little bit faster than just a regular grid search. I haven't done a strong comparison to see if really the output is the same, if they find similar metrics. It'd be a good test maybe for a future project. Do a grid search off. Okay, so we're gonna make our base search CV and we're gonna make that initialize that. We're gonna make it with our initialized model, our grid search, not fitted model, or initially. So we're gonna fit it afterwards after we have the parameter set up. We're gonna get our best underscore params, and then we're gonna get our best underscore score underscore. Technically, it was the scikit, so the scikit always has the underscore for attributes. Okay, so it's gonna take a little bit to run. We'll get started in a second. It's not too bad though to do this grid search, so we'll hang out for this. We're gonna go the next one. We're gonna do best underscore best. And so we're gonna assign our model. We're gonna fit this right from the very beginning. I'm just noticing here because I just turned off that fit in the model as well. What we're going to do here, we should actually do this. We should fit this model first. So we'll do dot fit, and we can go train, fit our model before we put it into our search. And then we want to use our model weight function. So we're gonna run. Well, so we're getting a little bit ahead. We'll let this finish running. Shouldn't take too much longer to finish. So just a couple more seconds, or hopefully less than a couple more. And so let's finish now. So we have our best estimator right here, and fit this model again and put it into our. Oh, so see, doing a little bit right now. I'm still making quite a few errors though. You can see a lot of errors right here, but I mean, an improvement for sure. So let's see. Now let's do our gradients. So the big one of the big differences in the gradient boosting versus the random forest is the learning rate. That's one of the things that are structurally very different about these two types of models. And lots of the other stuff is actually quite similar. So beige, search CV. what I'm going to then do is with my base search, I'm going to get my best underscore lens. I'm going to get my best to run that gradient boosting grid search right now. And while that's running, we'll get started on this. We're going to do our line. So we're going to do best underscore best to the underscore. And then because we turn off the fit right inside this, let's fit this the first time here. So we'll do GB underscore tuned dot fit. Okay. And so we'll do fit and we're going to do X train. And then we're going to do a model. Our final summary right here. And you can see that we have a slight improvement from me, or a decent improvement, not super good. The gradient boosting has the biggest improvement, roughly like 5 or so at percent, 5 points on the score. Okay, so not great. We're still overfitting quite a bit. We reduced it a whole bunch, but we're still overfitting a little bit. This is where we got the best testing score on our data set. So let's try some. Let's finish running versus grid search, and then we'll try some. Get onto the error analysis. Okay, now that we're finished our grid search here, let's do our best model, and let's look at what. So you can see we got a slight improvement on our team. They're doing basket. They do a little bit better. Grid searches are not magic though. We improved with the random forcing slightly, the gradient boosting a little bit more, but still the random forces are best model. So really, well, you can't really statistically say that one is better than the other at this point, but we'll try these two models. So we now have our models. We can do them a little bit better. So let's see where the errors are happening in this model. So we're going to predict our X test using our gradient boosting first, and then what we'll do is we want to use set index. So we're going to concat the predictions, the true values, that Y test with our X test, and bring this. So reset index, drop this, the same thing. Reset, paste, paste, and then we're going to put this all together. Okay. We're going to look where our errors are happening. And so this is going to make, so we're going to see where our errors are happening. And now we have our health index and our predicted values. We're going to see our errors. So we're going to make our error, which is difference between a predicted value minus the error. And so if the health index is above the error, this would be a positive, it would be a negative error, and then vice versa. So if we look at our distribution of errors, we're just going to plot dot histogram. Should we run this first one? And plot a histogram for errors. And see, we got some really big errors, negative errors, under predicted by a bigger Martian. We over predict, still not by a huge amount, but by a little bit. We look at the extreme errors. So we look at underestimated less than negative 28. Okay, so we got a few errors here. Kind of identified really methane, ethylene, and nitrogen. Kind of seem like there's something going on. Very different, very common, very large values here, but we really will get a better understanding. It's a little bit tedious. Describe. Describe. Okay. And then we're doing describe. Describe right here. So we're going to take the describe of this reduced one, the only with the errors, and we're going to take the dot describe. And so this is a handy because we can just very easily identify where are the averages really different right here. They're very big. They're not pretty small for most of these. They're very different for nitrogen, ethane, and methane. You can spend a lot more time on this, and you can really get lost in this, but this is just to get started, just to show you how we started. It's a very manual process to really identify which columns are different. But if we put a little bit of time to this, and we can really identify where our errors are occurring, we can usually find ways to improve it. So you can see here, another thing that we're identifying is the methane, ethane, are both 0 here. So when they're both 0, we seem to have weird predictions. So just to think, right, that when nitrogen is very high and ethane and methane are both 0, we seem to have kind of weird predictions. Let's engineer some of these features. Okay, so we want to make compositions of it. So we're dealing with our X to get started. Let's go back to our X. What we're going to do is we're going to go methane times X. And so this is a composition. We're multiplying this times this. Nothing super fancy, right? But now this gives our model a way to understand that these could be related and a way to behave differently if they're both, say, extreme values, both high values. There's something different about them. So, a composition of those could work well. Then we're going to make our one hot encoder. So we're going to say if X is equal to 0 and Y is equal to 0, we use the dot apply. So if methane and ethane, so methane would be 0, we're going to do something, and then if ethane is 0, we're going to also do something. We're going to return 1. Else, it's one of the things that you should actually highlight here. The errors are happening when there's 0. If something is 0, your model cannot do anything with it. Anything times a 0 is a 0. So your model just can't do that. So my thought process here is if I identify a one hot encoded feature that identifies when both of those are 0, our model just now essentially has some ability to do mathematics on the fact when it's 0. So just that simple thing could help. Or maybe there's something really different going on when they're both 0. Either way, our model will be able to now push off to use the fact that it's 0 to do this. And so I just want to highlight, we're going to do dot apply. We made a function, we use it with dot apply, doing axis equals 1, because we're going to want to go across this row right here. So we have 2 columns, we want to go across the row as we iterate. We're making a new math category right here. Do our train test, but again with our new columns. Train test. Split. And right here. Gradient boosting right here. So we do our gradient boosting right here. So gradient boosting compressor. We want to make sure that we fit the Bayes search CD again, and then we're going to fit it. And when this model is done training, you'll see what we want to do. Estimator best model best estimator, or sorry, best underscore s. Because we did change the model evaluate, we want to do our GB error dot fit x train y train. We're going to do that next here. You can see when that's done, making a little bit less errors. Our errors are not so extreme, especially on our tests that we really reduce the errors that are happening. When we do a random forest, progressor, we're going to make sure Bayes search CV, we're going to fit our Bayes search, and then just like that. So when this is done running, what we want to do is we want to do our best estimator underscore estimator. And then before we want to do our error dot fit x train train. Okay. So that, and when that's done, fitting, I put all the scores together again in another score, and you can really see here, it really just kind of magic, right? You see your train tuned or gradient boosting tuned, kind of low 70s sort of thing, or very, very high 60s. But when we've identified those errors, now we get a really extreme pronunciation of the 0.99. We've just been able to do a significantly better job with our predictions here using the error analysis that we did. Okay? So it doesn't usually improve it this much. This is a kind of a unique case. Highlights how important it is to do your error analysis. And you can see usually you can get pretty substantially higher if you keep iterating through the errors and constantly giving your model something else to essentially just push off. Give it a 1. All it needs is a 1. Your model will be able to use use that to make a better prediction. So thank you very much for joining me today, and I will see you for the next one.